Good morning, good afternoon, good evening, and welcome to AI for Good. My name is Bastiaan Kwast of the ITU, the International Telecommunication Union, and it is my privilege to introduce today's webinar, Explainability and Robustness for Trustworthy AI, by Andreas Holzinger, head of the Human-Centered AI Lab at the Medische Universiteit Graz, as part of the Trustworthy AI series hosted by Wojciech Samek, head of the AI department at Fraunhofer Heinrich Hertz Institute. For today's discussion, we will be using the Q&A functionality, which you can find at the bottom of the screen. Please post any questions for the speaker there. Additionally, there is the chat functionality, which you can use to communicate with other participants. Please make sure that you send your message to all panelists and attendees so that everybody can see your message. ITU is the United Nations Specialized Agency for Information and Communication Technologies, and also the organizer of AI for Good, together with 38 UN sister agencies and co-convened with Switzerland. With that, it's now time for me to hand it over to our moderator, Wojciech. The show is yours.
Thank you. I'm very happy to introduce Andreas Holzinger, our speaker today. So Andreas leads the Human-Centered AI Lab at the Medical University Graz. He is also a visiting professor at the XAI Lab of the Alberta Machine Intelligence Institute in Canada. And he is elected member of the European Academy of Science and the Alice member of the Alice Network. And he has significant contributions to the fields of interactive machine learning, explainable AI, trustworthy machine learning. So I'm very, very happy to have you here, Andreas, and I very much look forward to your talk.
Many thanks to Wojciech Samek and his great team for this very kind invitation. So AI for Good is a super important initiative. So I'm really very grateful to support it and to be allowed to speak here. So for the last 10 years, I've been working together with my group on generic methods to promote robustness and explainability and to foster secure AI solutions to provide human control over AI and to align AI with human values, ethical principles, and legal requirements to ensure privacy, security, and safety. So my name is Andreas Holzinger, and in the next 45 minutes, Wojciech will keep the time. I will make the case for why explainability and robustness are necessary components for trustworthy AI, and why we need it to help to reach these sustainability development goals. So before I begin, I would like to thank my funding agency. So Wojciech, the slides you can see?
Yes, we can see them.
Super, perfect. So I'm very grateful to the support of my FWF basic research project on explainable AI. I'm grateful to the European Union funding. So let's go to the agenda for this talk. So I will start with Sustainable Development Goals as motivation. I will show you some examples from the concept of precision. And then I will show you some challenges. Of course, there are some problems to solve. We call it challenges. And we will see that correlation is not causality and that sometimes a human in the loop can be beneficial. And this will lead us then to the concept of explainable AI or explainability. And we will end then with the concept of causability to measure the explanations received from four. So let's start. But before we go directly to the motivation, namely the UN Sustainable Development Goals, I would like to define the term AI just for a mutual understanding. So AI, the term AI is both ubiquitous and pervasive today. Even your waste paper basket is already AI today. So however, if we know what you are throwing away, we know a lot of you, so it should not be underestimated. So AI basically is one of the oldest fields of computer science and deals with the automation of intelligent behavior. So it is a very broad term. But the workhorse is machine learning, and in machine learning, this is clearly defined. These are algorithms that learn from data, can, for example, classify previously unknown things, reduce errors, make predictions, and so on. And they are run on digital computers, so digitalization is therefore necessary at the very beginning. And for a while now is a very successful family of machine learning algorithms, deep learning, deep neural networks. So And together with available data sets, they are really very, very, very successful today. Okay, let's start with the clear motivation, AI for Good, an enormous important initiative. So the concept of sustainability was born at the United Nations Conference on Environment and Development in Rio de Janeiro in 1992. This was the so-called Earth Summit. And this was based on international agreements on climate change and biodiversity and the Declaration of Principles on Forest Ecosystems. And this is really very important. And before we really begin, I would like to briefly define some terms well in advance for a better mutual understanding. So kind of an advanced organizer. So trust is subjective, of course, it's difficult to define, but it can be understood better when we consider that trust is evolved genealogically from some features of our human life. So with the aim that we can rely on other people to act cooperatively. Let's say it's a subjective expectation. Trustworthy AI, we can better define. It's just to ensure security, safety, and all the other things I've mentioned before. And here we should mention robustness. Robustness, we need a robust solution to be trustworthy. And many machine learning models achieve amazing performance, but on standard i.i.d. data. However, when we work in the real world with real data, they often fail because we have not this i.i.d. data outside. So explainability is very important because it can highlight decision relevant parts of machine representation and machine models. And explainability has one, let's say, disadvantage. It does not refer explicitly to a human model. And therefore, we have introduced causality as a measurable extent to which an explanation of a proposition to an end user, the human model, is or achieves a specified level of causal understanding. So this is the definition of causality. So this would be now the one slide summary of the talk. Okay, let us start with a big challenge which affects not only a few of us, but all. Everybody. So 10 million, this is, 10 billion. This is not the amount of our cells in the neocortex. This is the amount of people to feed on this planet by the year 2050. It's not so far in the distance. So we need to save our planet. When you eat, it's about agriculture. When you breathe, it's about forestry. And this is heavily dependent on the planet's climate, as we all know and we see on a daily basis. So what is a possible solution, or can AI help here? I love old scientific principles, and one solution to make use of a fundamental scientific principle is on a large scale is the principle of precision. And this I would like to introduce, give you some introduction to the concept of precision. Of course, I know technically accuracy, precision are always coming together, so be careful about that. But I will, let's see. The concept will become clearer when I give you the first example. So precision medicine. So the success of AI has enabled a paradigm shift from generalized medicine to precision medicine. A naive example would be we develop one drug and expect that it works for everybody equally on this planet, not taking into consideration that there are some differences in the biology, in previous patient history, in the context, and so on. So AI algorithms are now used for genomic sequencing and analysis from these vast amounts of biological data, and AI techniques can be used in many ways towards precision medicine. For example, to understand genotypes, phenotypes in existing diseases. So the big goal is to improve the quality and efficiency of patient care. So taking our naive example from before, to develop a tailor-made drug for one specific patient. But how can we use this concept on large scale for our goal to save our planet? Very similar, precision agriculture. Precision forestry has been around for more than 20 years. The basic idea is to enable more precise management of agricultural land. Because here we see heavy machinery, for example, heavy agricultural machinery. And the trends toward bigger, heavier machines leads to soil compaction. And this is not so good for the agriculture. So innovations through AI can help here. For example, helping to relieve the strain on our soil through more efficient measures. Soil is the basis for all life on our planet. I will show you a more concrete example in the next slide. So let's go down to soil. So hardware, as you know, is becoming cheaper, cheaper, and cheaper. Microsensors cost meanwhile very little. Everything is networked via the Internet of Things. The challenge now lies in the intelligent fusion of our ingredients. For example, the integration of data sets and relevant feature parameters. Here, for example, you see temperature, humidity, etc. So a good example for precision farming is also a drone, for example, which will, for example, provide targeted and very precise support, for example, in pest control. Precise means less resource intensive and therefore also, of course, more cost saving, but also for weather prediction, which is vital in farming. But let's go down even more to earth, to soil. So soil is the basis of our life, and various sensors collect huge amounts of data here, and with the help of our AI algorithms, we can extract features, temperature, humidity, etc. And the good example here is that every sensor is networked with everyone, with every other sensor, with computers and so. And therefore, you will see is privacy, security, safety a very important point. We will discuss this later on. So during my time as a visiting professor at the AIL lab at the RWTH Aachen, we have developed wearable sensors in the course of our Smart Health project together with Fraunhofer. So Fraunhofer is everywhere, omnipresent. And these sensors were used, for example, exactly in the same manner to localize, for example, to collect data. And they are meanwhile very familiar with us. So today you can virtually buy them in the supermarket. So such approaches are very versatile and can now be of great help in agriculture as well. So here you see precision farming at its finest. So for example, with wearable computing for plants. Such approaches are versatile and can help to localize, for example, corn rootworms more precisely and to take more precise defense measures, which is enormous important economically and enormous protecting our soil. So this is a big benefit. And let's look into the forest. Forest is very important for us. So we know that the bark beetle threatens the forest worldwide. And here AI algorithms can help to determine the condition of the forest and to make predictions about change of the forest, for example. And with such heat maps, we can, for example, get an insight. So the forester can not only analyze forest areas, but also apply protective measures more precisely. So the color scale here, for example, shows how and to what extent the trees are attacked by these bark beetles. But also forest fires are a new threat in Europe, never believed before. And here a very good similarity. For example, we worked in histopathology and here an histopathological image. And such an algorithm can now detect features in the data that the human being is not able to see. So they can, for example, detect how a tumor will develop, making predictions and so on. And this can be applied in forestry in the same way. For example, not only for forest inventory, as done here by my colleagues at the University of Alberta, because there is a huge risk for these wildfires in Canada generally, but in Europe also now. And they can not only detect it earlier, but also predict. And this data can be combined with all kinds of other data, air pressure, wind direction, wind speed. They can combine. So you see this integration, this data integration, data fusion. This is very important. And from this, we can then make predictions and take appropriate precautions, which is extremely important worldwide. And no talk goes without mentioning the pioneer work of Pierre-Simon de Laplace. This is my 101 starting slide, which should not be missed in any talk. So, because it's funny, because my student often cannot believe that there's something older than 10 years in machine learning. So this is actually the foundation of machine learning in 1812. So not 2012, 1812, 200 years ago. And this is very remarkable and should be mentioned. So you see the posterior is the likelihood times the prior through the evidence, and the inverse probability was the old term. This was called by Fisher, then Bayesian later on, and this allows us to learn from the data, to infer unknowns, and to make predictions. So, and this is very similar again into medicine. So in medicine, this has a long tradition because this is exactly how doctors make decisions under uncertainty. And you see here, we have a prior belief before making a particular observation, and then they calculate and they infer from this posterior. The posterior is the likelihood times the prior through the evidence. And of course, the problem for computers is that this normalizing, this division is usually very difficult. And usually, to be fair, we have a separation of knowledge and reasoning. But let's look into the success examples of machine learning. So we have this autonomous driving, autonomous monitoring, surveillance, hundreds of success examples. Of course, we have some challenges. You know, we do not have problems, we call it challenges. So let us first look at some interesting observations. So here we talk about adversarial examples. This is difficult for machines, but sometimes surprisingly easy for humans. Why? Because we as humans use abstract concepts. We don't need millions of data to tell it's a mob or a dog or anything else. So this might be funny, yeah, but we look in the following at a less funny example. So a bit of a history, this is perhaps the most famous example and maybe also a funny example. Network recognizes an image as a panda with a certain degree of confidence, then you apply some salt and pepper noise, and then so this is practically invisible to humans. And unfortunately, the network is completely confused. Suddenly the image, you see again a panda, but it is recognized as almost 100% as a gibbon. That may be funny, and this for sure a funny example, but what happens if this is within autonomous driving, for example? So for example, a stop sign is then suddenly recognized as a speed limit, and instead of stopping the car accelerates. And this is no longer funny. And this brings us to fundamental questions. Can we trust the results? Can we explain these results? Can we be sure that it follows rules? Can we be sure that it is resilient against perturbation or even attacks from outside? And can we generate new insights from this, for example, new knowledge? So adversarial research learning is a field on its own, and I just show this because it can, of course, fool both computers and machine and humans. But I'm going to show you also now a slide which I show my students right at the beginning, and you will see that these are the big challenges. For example, to learn from few data, to extract knowledge, to generalize, fight the curse of dimensionality, disentangle the independent explanatory factors of the data, and then to lead to this causal understanding of the data in the context. And context is the most important word here. And this brings us to Correlation is not causality, and I will show you what the human loop can do. So in our guiding principle in medicine, for example, it's very important that no correlation is without causality, and the challenge is to infer these causal relationships from this purely observational data. And this goes back to Hans Reichenbach, to the common cause principle. So I highly recommend the book by Hans Reichenbach. Very interesting. But I show you a practical example. So this paper shows that there's a high statistically significant correlation between stork populations and human birth rates across Europe. So even though it is evident to us that storks do not give birth to babies, this shows that an unreflective interpretation of correlations on p-values lead to very questionable statements. So we as humans have this knowledge, and this is exactly where the human in the loop can go into it, because when you remember this generalization error, so this is very difficult. This is very hard, and we can now let's say add this human experience. So you have seen now with this example, so people can often contribute amazingly well with this experiential knowledge, and this human experience can be very valuable and should not be underestimated. So no algorithm on the planet can currently replace it. Think of a forester in the loop who has an experience of 30 years, knows every tree, for example. So we would learn that from scratch. And this is relatively difficult. So this data-driven AI. So why should we consider humans? Because as I have mentioned, humans are able to understand the context. They can make inferences even from very little, even from noisy, from incomplete data sets. And they can learn relevant. This little word keeps me sleepless. What is relevant? So this is really hard. And often they can find the shared underlying explanatory factors. Of course, not always. So in many domains, both laymen and experts have to divide entities into binary classes. Yes, no, healthy, diseased, malignant, benign. And for many entities, this decision is not simple. So we need another class called maybe. And this contains a corresponding quantifiable tendency towards one of these two opposites. And here we have worked and proved that this is successful. For example, when using if-then rules, the human is often, I emphasize often, of course not always, to associate the input attributes with the output labels and can produce consistent rule bases. So the next is we have developed a novel approach for selecting network modules from multimodal feature spaces. And here again, our approach can be applied to different applications where this network structure data from the input and the corresponding nodes are associated with multimodal numerical feature values, as you can see here. And disease module detection in protein networks is a typical example of such an application. So, you know, proteins are the building blocks of life. So this is applicable in many problems in the life sciences. And this is very good, a very good example how we can make use of an expert in the loop. Yeah, and let us look where this is important. For example, disease module for classification of kidney cancer survival and non-survival patients, not an easy problem. So here you see the gene expression features of the certain genes, for example, HN, RNBK in the middle here. And now you have this CPSF4 above, and these genes have the highest importance values, which may further to point to a special disease effect caused by the interaction between these two genes. And the human expert can get insight by looking at this, and even by this counterfactual explanation, they can gain a lot of insight. Yeah, in summary, we can say that there's no debate that AI is currently extremely successful and exceeds often human levels for certain tasks. Unfortunately, most approaches are so complex that it is difficult to retrace and to understand how a particular decision was reached. So it remains open the question of why, and this question of why is often very important. And a few years ago, no one cared about these so-called black boxes. They just said, push the button, trust the results. However, due to this increasing social, ethical, and especially legal issues, the field called explainable AI is gaining extremely important. And this is due to mostly to the European General Data Protection Regulation, which explicitly mandates a right to explain, which should also not be misunderstood, because it does not mean that everything and each fact must be explained in a timely manner. It means that upon request, for example, when something happens, when something goes wrong, there must be a way to retrack, to understand, and to replicate why the algorithm came to a certain result. So it's about trust, it is about verification, it's about legal aspects, keeping humans in the decision-making process to assign responsibility. So the XI community has beautifully developed a whole range of very useful techniques. Let us look on a few of them. So for example, one side, the community is working on interpretable models. Those are anti-hoc interpretable, so-called glass box models. So for example, regression, naive Bayes, decision trees, graphs, they are theoretically interpretable, but also a large graph can be very complex, but it can be interpretable in principle. Whilst for the other side, we have this so-called black box model. We need what we call post-hoc models. So post-hoc explainable AI methods for this interpretation. And that is one thing. And the XI community has a bunch of very successful methods. For example, gradients, you can start with function-based methods, or you can do sensitivity analysis with the Turpin model, and then we see how robust the system responds. Of course, this can measure only local effects, but often we need the global effect or the global behavior. Then simple Taylor expansions, for example, this is a decomposition approach. The computations are decomposed into a set of localized neurons and then can be recombined, similar as an error feedback. So mathematically, this is by using the chain rule for the derivatives, and this goes back to Taylor series, introduced in 1715 by Brooke Taylor, who lived in Edmonton, Middlesex, England, in good old Europe. Edmonton, Canada was not existing at this time. So, but there are a lot of other methods, and I'm belaboring the obvious because Wojciech is a pioneer in this field. And Wojciech's team has developed very, very powerful methods. The most famous one is layer-wise relevance propagation. And I have to show this for the sake of great appreciation of this method. And recently, for example, particularly in the medical field, we don't just have this pixel-based data, such as images. We have a lot of data which can be represented as graphs, for example. Consider proteins, the building blocks of life, and from such proteins, which are openly accessible in protein databases, experts can infer secondary structures, and from these we can derive sequence graphs. And here we can also apply the powerful tools that graph theory offers, and one method is LRP, works also on graphs. So very, very good work by Wojciech and his team. So here, some of our work. Here in the middle, we see a histopathological image. You see a benign non-tumorous area, the malignant tumorous area above and below. So this is marked by red dots. So if a pathologist evaluates this, she or he intuitively sees with one look that the explanation of the AI solution is correct and sufficient. So we say in this case, there is congruence between machine and human. However, if we look at the example below, just press the button. So here the same visualization method is applied, but now the AI solution found wrong tumor areas. You see this in the middle here. In this case, we have incongruence between machine and humans. And this is important because now we can highlight this via these methods, which otherwise would not be visible for the human. And the AI would make a definitive error. So this is very, very good. And this is a very generic approach. So this can be applied for the detection of bark beetles in a forest or rootworms in a cornfield. So, yeah, you have seen now with technical solutions, we can make these black boxes interpretable, for example, via producing a heat map to enable an end user to interpret what features were most relevant for a classification result. And explainability is very, very good. It is a first step. So explainability technically highlights decision relevant parts. That means parts which contributed to model accuracy in training or to a specific prediction. And we have observed how human pathologists make diagnoses. So human experts proceed in two phases. They describe at first what they see and they use special terms. For example, they talk about objects, very interesting. There are cells, for example, this is an architecture, portal field. Here, the cells are closer, smaller, closer together. It might be a tumor, but it can also be an inflammation. So we need this contextual understanding here. But this is very important because the missing ground truth, and ground truth is information provided by direct observation. This is this empirical evidence in contrast to information provided by inference. So ground truth is really very important. And I skip this for time reasons. So Wojciech, you have to give me some time hints. How much do I have left?
Yeah, 10 minutes, 12 minutes. 10
minutes, super, perfect. Thank you very much. Okay, so all this inspired us to develop experimental environment, Kandinsky patterns, but first I explain where the name comes from. So we named it after Vasily Kandinsky, a Russian painter. I'm highly interested in this art. And Kandinsky analyzed these objects not objectively from the point of view of physics, but from the point of view of the inner effect on the viewer, from psychology. So he described that there are basic shapes from which more complex compositions can be built. Actually, and I should note that he did at this time, when compositionality of the visual sense had not yet been empirically researched, he mentioned these compositional effects. And this was in 1923. So this is really very amazing. Many decades later, in 1962, Hubel and Wiesel conducted their famous experiments that later inspired the deep learning folks around Rumelhart, Hinton, Williams, later Lecan and Benji and so on. So this is very interesting that Kandinsky already was inspired by this compositionality effect. So our world is compositionally, which was the 1962 experimentally proven. And I show you an example, and this might also be funny, but has a very important background. So in our Kandinsky patterns experimental environment, we can create concepts together with the ground truth. For example, here, true statement. So here you see the cells are smaller, closer together, could be a tumor, but it depends on the contextual understanding. Or a false statement. So here a complete random pattern, or a counterfactual statement. What if the cells are slightly larger? Then it could be more an inflammation. So you see these counterfactual statements. This is really very important from part of explanations for getting insight into such behavior. And of course, this is important that this is understandable for people on paper. So here we have also this in a booklet form. And this I should mention for the sake of completeness, this is from the very famous Gödel-Escher-Bach book. So on page 649 or so, you can see this image. So these are the so-called Bongard problems, and they go also back to a Russian, Mikhail Moisevich-Bongard, who died in 1971. And these are a kind of geometric puzzles. So the problem consists always of two sets of 6 drawings, as you can see here. So this is a typical Bongard problem, but this is very different to our Kandinsky patterns. Much better known as the Bongard problem is the clever data set. So this is also different from our Kandinsky patterns because our concepts address groups of objects and the clever concepts do not. For example, the left off, right off. They refer to a pair of objects in the scene that need to be discovered. But in pathology, for example, you do not compare a group of scenes. So this is less appropriate for medicine, but very appropriate, of course, for all kinds of visual reasoning, for example, moving objects. And there is also another related word, cleverer. For example, this tests causality reasoning with collision videos. So this plays a major role for autonomous vehicles, or also for trajectories of missiles, for example, but also no high priority for medicine. So because our concepts address these groups of objects, left off, right off, etc. And another work is called Bongard logo. Therefore, I've shown Bongard before. So now this was recently presented at NeurIPS. So here are many small objects that are convex to each other in one group, and in the other group, they are non-convex ones. And this is similar to, in principle, with Kandinsky patterns, but also here the question, is it relevant for histopathological diagnosis? It could be maybe important. So we can make a distinction between convex and non-convex sets as well. Okay, but it's in our case, it's not so much emphasized. Okay, and of course, recent work around Brandon Lake from Facebook AI Research, CURI is short for Compositional Reasoning Under Uncertainty, also very interesting. You can play around. Our Kandinsky patterns are, of course, open, freely available to the international research community. So in short, they are mathematically describable, simple, self-containing, controllable test data sets for developing, validating, training, explainability. Okay, measuring the quality of explanations. So a recent result of our research is the measurement of the quality of explanations. And here again, causability is neither a typo nor synonym for causality in the sense of Judea-Pearl. So causability is in reference to usability. So while this explainability is about implementing transparency and traceability, causability is about measuring the quality of explanations. So the concrete definition, causability is the measurable extent to which an explanation of a statement to a user achieves a specified level, this is important, specified level of causal understanding with effectiveness, efficiency, and satisfaction in a specified context of use. Context is very important. And of course, this is the basis for new human AI interfaces. These interfaces should enable exactly this contextual understanding and allow the domain expert to ask questions, and also this very important counterfactual what if questions to gain insights. And here the human in the loop is very important to bring in this experience, this conceptual knowledge into this whole pipeline. Yeah. This is our model. So when is an explanation good? Obviously, when it has been fully understood by the recipient. But we know all that is not easy. And you all may remember Paul Watzlawick. This is the Austrian communication scientist born in Villach, Austria, who worked at the Mental Research Institute in Palo Alto in California. You remember for sure his 5 axioms. The first one is you cannot not communicate. So let's start to quickly explain here our model. So we start with the statement. This is the statement from can be made either by a human S index H or a machine S index M, where S is a function of R, K, and C, and we define R is a representation of an unknown or unobserved fact, U index E. This is the unknown. With respect to an entity, the unknown, yes, and K is the pre-existing, the pre-existing a priori, we should say a priori knowledge that is quasi embedded in an algorithm for the machine. Think on the LRP method, or in a human. So this is the one side, the physical context environment, the context in which the decision was made. So we call this the pragmatic dimension. And U index E, now the unknown or unobserved fact, represents a ground truth, GT, which we try now to model with machines, M index M, or as humans, M index H. And these unobserved or unknown, hidden or latent variables can be found, for example, in Bayesian models, in hidden Markov models, and methods such as probabilistic latent component analysis. And the overall goal is to determine whether and to what extent a statement is congruent with the ground truth and the explanation of a statement. So for more details, you can refer to the paper. I hope that I'm still in time and can now come to the conclusion. You know, you can speak about everything, but keep within time. So one last example from medicine should serve as for the summary. So modern pathologists do not look only at histopathological images, for example, morphology, but they look also on all sorts of other data, molecular data, all sorts of omics data, genomics, proteomics, metabolomics. So, and of course on the patient history, this is a medical history sheet, which is ultimately text. And then they make decisions. And as I mentioned at the beginning of this talk, many factors contribute to an outcome. And it would be interesting now, from many points of view, to remove or change some inputs and see what if, how does the result change? For example, how robust is my system against alterations or disturbances? And this is the goal of multi-model causality, to measure what changes how when something is changed. And you see, robustness and explainability is in the focus of this so-called human-centered AI, because we want to make sure that the human is in control and that traceability, transparency, and comprehensibility are always ensured, so that it is, of course, promoted trust. Okay, and I come to the last slide. So our central topic is to design, develop, and evaluate robust and trustworthy AI. And we have recently published a vision paper on and this is important to all fields, so that impact human life and agriculture, climate, forestry, health. So this is an integrative process chain, cross-domain, cross-disciplinary in a joint effort. And we have localized here 3 frontier research areas. So area 1 are complex networks and their inferences. I have given you some examples in my talk. Then graph causal models and counterfactuals. I've also given you some examples. And then, of course, verification and explainability methods to have trusted decision support. And this is important in the future to explain why a certain AI decision has been reached, to ensure trust. And now my final slide. AI can help to solve major problems on our planet. Yes, to foster secure AI solutions, we need robustness and explainability. And human-centered AI is a way to ensure to align AI with human values, ethical principles, legal requirements. This leads to the acceptance and trust of the users. And all this should transparently support and complement humans. Thank you very much to you for your kind attention, and I will give now the virtual microphone back to my moderator, Wojciech.
Thank you, Andreas, for this very interesting presentation. So we now have time for questions. So do we have questions from the attendees? So maybe I can start with one. About your intelligence tests. So how intelligent is our AI nowadays? How can you measure it? And can we compare different architectures? Are some architectures more intelligent than others? Or yeah, maybe you can elaborate a bit on that.
This is a very difficult and also philosophical question. So this would be better stated to Alan Turing, for example. But I have here a recent from IEEE Spectrum, why is AI so dumb? Yeah. So yeah, this is amazing that the more we learn about machine learning, about this artificial intelligence, we learn that we have limits, of course, and we must clearly determine, to be fair, which problem we want to solve. So in high dimensional spaces, algorithm, of course, beat every human because we cannot look into higher dimensions. Yeah. This is amazing that AI sometimes can detect something which the human simply does not see. So this is the big benefit. Of course, when it comes to context, to contextual explanation, to this understanding where you have this experience, you, Wojciech, have this experience, you look with one view, you don't need millions of examples, you see it with one glimpse in your eye, and often you are not able to explain it, yes, but you know it. And this is amazing. So humans are awesome, and I like humans, because they are real problem solvers. But I think in the future, and I think this is the best answer I can give, in the future, both will be important. So you will complement each other. So for maybe the human in the loop is then in the middle, and we can complement the statistical machine learning approaches with logical symbolic approaches, which are also very useful in certain problems. But the concrete answer to your question is, it depends.
Do we have questions from the audience? Then maybe I have another one. So I think this is very important to have like the human in the loop and to consider the whole system, like both sides. And I also read some work where people showed or claimed that explanations of transparent systems can have the danger that the human will think that the system is transparent, so it knows what it is doing. So what is your experience and your opinion on that? So do we also need to train humans to read the explanations and to know the limits of AI?
Thank you for Wojciech. You are the most clever person on this planet. So this is a great question, and this leads us to bias, fairness, trust. So you see how important this aspect is. Absolutely. So 100% agree. We need this to make this awareness, because, you know, there was always the danger that we trust and rely on machine decisions without reflecting on, could it be true, or is it true, or to what extent is it true? So, and this, I think, is genuinely human. And I think this is a great thing to have this awareness of the limits and to make it. And I think the explainable AI community is exactly in this direction: fairness, bias, trust. This must be researched, and this must be solved. Yeah, absolutely.
Okay, so we have some questions from the audience. So one is, in your opinion, how will the proposed EU AI Act put pressure on the XAI research field?
You mean in a positive sense, put pressure?
Or like how will XAI enable participation of users and the society in the development of AI systems?
Yeah, I think this is intended so that the society, the stakeholders, different stakeholders should be included. For example, patients in medicine, farmers in agriculture, and so on, and foresters, for example, in forestry. Interestingly, for example, these AI laws and the legal statements which Europe has implemented are very stimulating the community, because I can clearly remember, Wojciech, this was maybe 10 years, meanwhile, time is going so fast. 10 years ago, I held a lecture at Carnegie Mellon, and I talked there about this explainability and this human in the loop. And they said to me, really, they said, Andreas, we are not interested in a human in the loop. We want to do it automatically, fully automatically. Press the button, wait for the results. That's it. But I understood years. I was very depressed at the moment because nobody was interested in my research. But then I realized that they were talking about autonomous driving. And I agree with them completely, because in autonomous driving, the human is really the disturbance factor, because think of a drunken Berliner taxi driver. He would disrupt the whole working system, because an autonomous car, theoretically, will hold the speed limit. They will detect oil leaks on the street. Yeah, you, Wojciech, you drive your 140 kilometers an hour, disregarding whether there's an oil leak or not. Yeah, so this is risk, and humans are risk takers. So they ignore often some cuties in the street. So I think autonomous vehicles will work if everything is autonomous. Yeah, so every car is autonomous and no human disturbs this with breaking the rules.
Yeah. We also have another interesting question about explainability. So how explanations should impact in decision making, how they can be used in humans, because in other applications, when you have, for example, error bars, people rarely use them in decision making. So if there's uncertainty, even if you know them, you're often like not really using them in decision making. So how can we make sure that explanations will give some additional benefit in decision making?
Yeah, great question. And this always, the answer is, it depends on what you really want. For example, think of a medical doctor. They must trust on the device. They cannot always take an explanation into account, and because then time is a critical factor, but they have to trust. But in case something happens, there must be a way to retrace, to replicate, and to understand how the decision was made. For legal reasons and for ethical reasons as well. But on the other hand, you have, for example, this knowledge gaining aspect, for example, to get insight. So look, we always look only on the end user side, the medical doctor, the forester, the farmer. But look at the development. At the designer and developer, they can really get insight into behavior when developing. So explanations can really be beneficial there on the development side, to get a better understanding on how to develop the algorithms. So I think this depends on where you sit.
And like in the histopathology use case, so what would be the benefit of explanations? Would it like be time saving of the doctor, or would they make better decisions, or?
Both. So first of all, you need this quality control. Yeah. Secondly, you need to have this human in the loop, because when an explanation is given, you can, for example, be sure that this is the case. So this is quality again. And and I think also insight, because interestingly, the medical doctors can also learn from such algorithmic behavior. And ideally, an algorithm could also learn from the human in the loop. So this is in the future maybe an impact. So to have a computer in the loop, yeah. So you make constant decisions and you have a computer in the loop, and the computer learns from your decisions. But again, and this leads back to the first question, again, you have always this bias, the danger of bias, the danger of fairness, because also humans are not unbiased, you know that.
Yeah.
So there, so and you know, this is not so easy as it seems, yeah.
Yeah.
And you see, IEEE spectrum, yeah. Why is AI so dumb?
That's a good title. Okay, so unfortunately, we have time for one last question, and we need to finish. So, are there skills in the future that must be limited to human intervention only?
This also depends, for example. So when we take the autonomous driving as an example, it's not necessary that the end user understands the behavior of the engine in detail. Yeah, this is left to the mechanics, technicians. Yeah, but for example, if you want to get insight into a certain things, into a certain problem, then it is of course necessary. So it depends completely on the problem. Yeah. Mm-hmm. So not each and everything is necessary to have explained. You simply take it. So it depends.
Okay. Yeah. So thank you again, Andreas, for giving this very inspiring talk, and I hope to see you soon in real life, in person.
Absolutely. I'm very grateful for your initiative. So sustainability goals, I was fascinated for a long time by it. So I fully support this. So I think these UNO sustainability goals, development goals are very, very important, and it is necessary. We all must help together to save our planet. We have only this planet, and we must ensure that your children and your grandchildren, Wojciech, can still live in a very nice planet. So let us all help together to save our planet.
Okay. Well, thank you.
Thank you, Wojciech, and a big thanks to Andreas Holzinger, our speaker today. We hope that you enjoyed today's webinar, and we're launching a quick poll that should now be coming up on your screen. And in the meantime, let me say a few things that may be of interest to you. We have a seminar tomorrow on health and AI in our AI and Health series. Nigam Shah, professor of biomedics at the University of Stanford, as part of a series hosted by Isaac Cohen, who's the chair of the Department of Biomedical Informatics at Harvard University. And please, and on 5 of January, we have a seminar with Suman Rafuri from DeepMind. So you can find the links in the chat. And for anything, please have a look at our website, aiforgood.itu.int. And with that, thank you very much, and we hope to see you soon.
Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector.